This is a video covering the instruction set of my relay computer, and it's the second in a series of 2020 update videos. Last time I covered off the architecture of my computer, and next up we'll be looking at the assembly language, and then programming, and then followed by a tour of the computer and a demo of it. If you saw my video last time, here's where we got to. This is the architecture diagram of the relay computer and shows all the various functioning groups. Now, so far as it stands, we could control the computer manually, so we could load and select values out of the registers, we could operate the ALU, we could operate the memory, and so on and so forth. But really, a computer needs to be able to run itself, given a list of instructions that we want it to perform. Now, this is where the instruction register comes in. The computer can run line by line through a program in memory, and each line of the program is effectively an opcode, which is an 8-bit value that's loaded into the instruction register. It's this 8-bit value that tells the computer what to do each time. So an example of that may be loading a value from a register to another register. So in this case, maybe selecting register A and then loading register D, or maybe selecting register M1 and then loading that into Y. This is what's known as an 8-bit move, or a move 8, because it can move 8-bit values, or rather copy 8-bit values between different registers. Likewise, we can copy values between the 16-bit registers. So in this case, we're selecting a value from J and loading it into the XY register, or we can select a value from M into the PC. Now it's interesting here actually because the J register can only be selected, and same with the M register, we can't load back into those, so they do have a limitation. It's only the XY register that can be loaded and selected. Now the move from M to PC is quite an interesting one because any value that we load into the PC will effectively change where it's going to get its next instruction from. And this is basically how branching works, by taking a value that's in the J register, the jump register, and then setting that to the program counter, as we'll see shortly. But anyway, this class of instructions is called 16-bit moves, so it's the move 16 instructions. So what else can we do? Well, obviously we've got the ALU at the top. We want to definitely be able to use that because that really is the heart of the computer. That's the bit that allows the calculations to be performed. Simply with those, we'll just have a class of instructions called ALU. So next up, we probably want to make some good use of that memory. So the way this will work is it would need to load an address onto the 16-bit address bus, like so. And that then means then we can load values on and off of memory. So we could load a value from a register into the memory or load a register from the memory. These are effectively the load and store operations. Now, we did talk recently about branching, which is something that the computer's been working towards. So this is a case where we'll take a look at those condition flags that come off the ALU, so the 0, carry and sign flags, and then based on those, if it matches a certain condition that we're looking for, we can load the program counter from the jump register, and that's effectively how the branching works. So these are all the GOTO class of instructions. So far, one problem we have is actually getting values into the registers. So we can certainly load things into, program things into memory to begin with and then copy those values over, but it's often quite handy just to load a value directly into the registers. And this is often quite a quick operation to do. So say for example we might have the number 8 that we just want to put straight into register A. Well, these are the set class of instructions. They just allow us to quickly load a value, and they're very frequently used. So this is just our basic class of instructions, and there are extras as well. So there are a few more we might want to make use of. So we might want to make use of that 16-bit incrementer to, say, for example, increment one of the 16-bit registers. Also, there are other smaller operations we want to do, things like halting the computer, for example. We can't do that at the moment, but eventually we want to be able to stop the computer. We'll need an instruction to do that. But how do we go about laying these instructions out? So if we think about what that opcode at the top actually represents with the 8 bits, is actually that gives us 256 permutations of codes. So we could do 256 different instructions, which actually sounds like quite a lot. Now the way this table's laid out is, if you take the bottom 4 bits of the opcode and convert it into hexadecimal, that gives you the numbers 0 through to F on the top. Likewise on the left hand side, if we take those values 0 through to F, that gives you a grid down the left hand side. So effectively that's how we're mapping out that instruction space. So let's start with a nice easy example to begin with. We'll go for the move 8s, and we could say it's desirable that we'd like to be able to move a value between A, B, C, D, M1, M2, X or Y. So they're our general purpose registers, and we want to be able to move a value between any of those. Now for each one we'll have a source and we'll have a destination, and for each one there's 8 options. So that really just gives us an opcode as follows. So we need 3 bits to define the source register, and we need 3 bits to define the destination register. And that's because each one has 8 permutations. 3 bits will give you 8 permutations. So that basically gives us our code. And if we prefix that with 0, 0 and add that to the map, we can see that we've used a quarter of the space already. So already we've only done one instruction and we've already used a quarter of the space. So clearly we need to be quite picky about how we do these. So how about the set one? And again, we can see with the code we're going to be a little bit limited on how big a number we can bring in. We obviously can't bring a full 8-bit number in because that will leave us no space at all. If we bring a 7-bit number in, we'll need half of our address space. So if we take a look at the code for that, we can see we've actually gone with 5 bits for the value. Now, if we had 4 bits there, we'd be able to do a value up to 15. But the extra bit is actually then to do the minus sign, so effectively do 2's complement. So with this then we can actually load a value between 15 and minus 16 in. The last bit then is just to select which register we want to put it into. So in this case we'll do A or B. Now if we want to do A, B, C or D, we'd need 2 bits to put that value in, but again then we'd take up half of our address space. So you can see this is the reason why we only use 1 bit to define the destination register rather than 2. And if we transfer that over to the diagram, you see that's now half of our instruction space gone just on moving values between registers and setting a value. So already we've got very little left now to work on the rest of our instructions. And you can see then why you need to be quite picky again with how you lay these instructions out. Let's work through a bit more of a complicated example then. So if we look at the GOTO example, so we've got our 8 bits, how are we going to lay this out? Well, first of all, we can see that given the condition registers, we're going to need 1 bit for each of those. So we need 1 bit to say if it's a sign, 1 bit to say if it's carry, 1 bit for 0, and also then 1 extra bit for not 0, because sometimes it's useful to do 0 or do not 0. So that's 4 gone already. What could we do next? Well, as well as branching to an instruction, sometimes we might want to save the address of the next instruction before we do that. This is useful in things like subroutines, where you'll go to another location in memory, and when you're finished, you'll jump back to where you came from. So we need an option to say whether we're going to do that or not, and we use the last bit there to say, do we want to load, say, the XY register before making the jump? So we've got the basics of branching here, but actually we might be missing a trick, because the way the jump works is it will load the value into the J register, so it will load the upper 8 bits into J1, then the lower 8 bits into J2, and then optionally take a jump. But we can also use it to load the M register as well, and effectively this will give us like a 16-bit load immediate. So we won't take a jump in that case, but we'll just load it into the memory register, and that's just another way of using this function. And to do that, we just have 1 extra bit on there, D, to say is the destination register going to be J or is it going to be M? And that just gives us a bit more flexibility. And that's basically it for that instruction. There's not really much more we need to do, so we can just prefix that then with 1, 1, and that's the bottom bit of our space gone. So you're starting to get the idea now. Last example we'll do here before we move on is the ALU instruction. Now fortunately for the ALU, we know actually there's 3 bits required for the function code, because again it's got 8 operations it can do. So if we bring that on here, the only other one we've got then is a destination. So again, we've got a choice here again. Do we want to be able to load just 1 register, 2 registers, or 4 registers, depending on how many bits we're going to use? Well, again here I can see that really I'm running out of space now, so really I want to be a little bit more economical now. And in this case, we'll just have a 1 bit to define the destination register, which basically gives us a choice of 2 registers, and in this case we'll use A or D. Now that's actually quite handy, because we know in this case we can't load B or C, because that'll backfeed into the ALU. So really we've only got a choice of A and D if we didn't want to go into things like M1, M2 and so on. So if we transfer that over, you can see that we've taken another stripe out of the map. So you get the general idea now. So let's move on, and we'll move on to the actual instructions set that we've got for the computer. So you can see how these have come about. Now let's go through the instructions themselves. Now I'm only going to talk about the instructions we've actually got implemented in the computer so far. So as I add further instructions to the computer, I'll cycle back on them on my blog. and also I'll update the video for the next time I do an update. So for the moment we'll just run through the instructions that are actually feasible and possible today. So let's start for that move. So the move 8. So look at the bottom left hand side there, you can see you've got the name of the instruction or the class of the instruction, and then next to it is the amount of clock cycles it takes to operate that instruction. So in the case of move 8, it's only 8 cycles, so it's one of the quicker instructions, but some of the instructions do take a lot longer, and this is again why you want to be optimal in which instructions you're using. You want to try and use as much of the quicker operations as possible and only use the longer ones when you really have to. In the blue there in the middle at the bottom, we have the opcode. So in this case you've got 3 bits for the source, 3 bits for the destination, and then the leading 0, 0. And the 0, 0 is what the decoder will use to identify that this is a move 8 instruction. So if we break these arguments down, as you can see here is all the options for the source register and destination register. So you can see the options for A, B, C and D. Note that the further options are greyed out because they're not implemented at the moment, but effectively once I've sorted those out, you'll be able to copy values between M1, M2, X and Y, as well as A, B, C and D. Right, so let's find a way of listing these. So what I'll do is I'll quickly pop some stripes down the right hand side, and then we can pop the current code we have there in the first entry. And as we add more instructions, I'll pop them in there so you can see them and compare them against each other. Right, moving on. Let's take a look at that load immediate SETAB instruction. So again, this is another 8 cycle instruction, prefixed with a 0, 1, and then we've got an R for the destination and 5 bits for the value. So the value's in 2's complement, so you can load a value between -16 and 15. Now you might be wondering how that actually works, because obviously normally a number's only negative if you consider it that way. But the reason why this works is because it sign extends. So if you take an example here, we've actually got a number 0, 1, 1, 0, 1, and you can see it just sign extends that 0 all the way to the left. Likewise, if we do an example here where we've got 1, 1, 1, 0, 1, you can see it sign extends the 1 all the way to the left, and that's basically how the values get loaded into the registers. So we pop that over on the bottom right there, and now we've got 2 instructions in our set. Right, let's move on to the ALU. So again, this is another 8 cycle instruction. As we saw before, it's prefixed with a 1, 0, 0, 0 in this case, so the only bits we can change are the last 4 bits. And they are the destination register A or D, and then the function code. So by default, it just clears the register, but then we can select add, increment as our arithmetic operations, or then we've got the bitwise logical instructions and, or, XOR, not, and shift left, which is actually a rotate left. Actually, that's you might see that labelled differently on some of my different slides, because actually it will rotate the value round all the way. Let's have a look at some of these in a bit more detail. So for the add, basically here's a truth table. So if you think of the inputs B and C, and then a carry in marked as I, you'll get the result and then a carry out. Going right over to the very far right of that diagram, if we've got B and C set to 1 and we're carrying in, then effectively we're adding 3 bits together, which gives us a result of 1 and a carry of 1. In my last video I went through a little bit more about how the binary arithmetic works, so if you're not familiar with this, by all means pop back to that video and take a look at that. Increment's quite straightforward, so in that case we're just going to add 1 to whatever's in the register B. So here's an example where we're adding 1 to it, and you can see basically it's rippling the carry through to the 3rd bit from the right, so the ending of that becomes 1, 0, 0. Here's an example of carry on an add. So here you can see actually that the carry only starts happening at the very last bit, so the most significant bit at the left, where we're adding bit 1 and bits 1 in B and C, so the result is 1, 0, so the 1 carries through. And this is an example of where the ALU would set the carry flag on this case, so that you know when you've done the operation that there was a carry. This is really important, of course, if you're doing something like 16-bit addition, because now you need to carry that bit over to the next addition when you're adding the upper 8 bits. Fine then, here's just one more example of the adding 2 numbers together. Right, let's move on to taking a look at some of the logic operations. So again, truth table wise, the AND works like this. So you can see that the result is only 1 if both B and C are set. OR works when B and or C are set. So this is the inclusive OR. Following that then we have the exclusive OR, which sets the result bit if B or C are set, but not when both are set. Not's quite nice and straightforward and only operates on the B input, so if B is 0 the result is 1, and if B is 1 the result is 0. Shift left then, or really this rotate left, as you can see basically moves all the bits to one place left and takes the leftmost bit and puts it back at the far right. So it's almost like they're on a conveyor belt, if you like. And this is quite a useful operation as well. You can compose a lot of these operations together to make more complicated functions. And certainly things like if you wanted to do a shift right, you can just do that by repeatedly shifting left. So there's a lot of these functions you can compose together and make more complicated functions. Okay, so that's it for the ALU function. So update the diagram on the bottom right there, and you can see then we've got our opcode starting with the prefix 1000, and then we've got our options for the various ALU functions. Right, branching. This one is the GOTO class of instruction. So the GOTO is quite a long function at 24 cycles, but that's because it needs to load the J register or the M register before actually doing the operation. And that takes quite a long time. It's also got to move through 3 blocks of memory, so it has to load 8 bits into the upper part of the register, next 8 bits into the lower part of the register, and of course this is all after actually loading the opcode itself into memory in the first place. So quite a complicated instruction. Options wise, we just saw earlier on, we have the destination going to M or J, then the options of jumping on sign bit, carry bit, 0 bit or not 0 bit, and then finally the option to load the XY before taking the jump. Notice that the S, C, Z and N is that they're all inclusive ORs. So if we did C and Z, really what we're saying there is we will take a jump if the C flag is set, or we'll take a jump if the Z flag is set, or if both are set at the same time. Now there's no AND here, so we're not saying it's going to be C and Z, these are all OR. So for example, if you do ZN, what you're saying there is take a jump if it's 0 or if it's not 0. In this case it will be one or the other, but it will always be at least one of them, so the result is you'll always take a jump. Alright, so the opcode there as you see it, as I say, isn't the whole story. So actually there's always 3 parts to this. So you need to give it the opcode, and then the next location in memory needs to hold the high part of the address that you're going to jump to, and then the next 8 bits hold the low part of the address that you're going to jump to. And effectively this is what's then loaded into the J or M register, and that's what it will use to take the jump. Effectively the idea is if you do take a jump, it will load that value into the program counter, and that will effectively point you to that new location into memory. There are some specific examples of this as well. So if we look at general branching, it would take this form like this. So you would have a double one, which is the code that identifies this as a GOTO instruction. But then we're always going to load the J register because that's the only place where we can actually do the jumping from. It has to be the J register. And in this case, we're not going to load the XY. So all we're actually left with as options are those 4 bits. And if you look at a permutation of those, here's actually all the different options you can do with these. So there's quite a lot of choices. So if we set them all to 0, then we're never going to jump. So yeah, you've now got the J register with the address in, but you're not going to go anywhere with it. Although that is a special case we'll come to shortly because it does have its uses. Next on then is branching if it's not 0 and branching if it is 0. And now these are useful if you actually do an XOR operation with B and C. If the values are exactly the same, all their bits will be the same and the result will be 0. So we can test for comparisons and XORing them against each other. And if the value is 0, they're exactly the same. And if it's not 0, they're not the same. And this will be really useful when we're doing programming. Branch OR, as we just mentioned, which is making a jump if it's 0 or not 0. And then we've got into some of the other ones. So we've got carry, basically after an ideal or increment, carry or not 0, carry or 0, negative, which can also mean less than as well. So if we're treating the number as a 2's complement, we'll know that it's negative if it's got the sign bit set, the leftmost bit. Second then we've got negative or 0, which is less than or equal, if you're using that same way. And then finally we've got carry or negative. So there's a couple of options there. Here's another couple of specific cases. So we've got the 16-bit load immediate at the top, which is effectively loading the M register and not taking a jump in the slightest. If we wanted to load the J register but not take a jump, then we just take the third bit from the left to a 1, and that would load the J register without taking any jump. Just below it then we've got the jump always. So in this case we're loading the J register and jumping regardless. So that's basically a forced jump. And the last one there is call subroutine, which is there basically where again we're going to do the jump regardless, but before we do that we're just going to copy the current value in the PC into the XY register so we've got it for later use. Now at the moment we don't actually have the instruction to do that back again, because what you need to do at some point is move the XY value back into the program counter. And what that'll do is that'll basically restore that value. Now at the moment we don't have what would effectively be a 16-bit move. That's not implemented at the moment. So really we can't actually do subroutines yet. But once that's there, then we can do those. Right, so pop that in the bottom right and there's your GOTO instruction, all ready to go. So that's it actually for what the computer can do at the moment. So you can see in the list there we've only got 4 items and there are 5 slots empty. So the question is what will go in those? So on my blog I went through the design for the decoder recently, and that's the card that will decipher which one of these instructions it is based on those leading parts of the opcode. And if we follow the diagram along, you can see 0, 0 gives us a move 8, which at the bottom right you can see that corresponds with the 0, 0 down there. 0, 1 is a set and 1, 1 is a GOTO. Of what's left, we know that 1, 0, 0, 0 is the ALU, so that's taken care of. So now we're just left load and store, which is to load and store values in memory, M16, which is a 16-bit move, and then at the bottom there we've got the inc, which is increment XY, and that allows us to do a 16-bit increment of the XY register, which is useful sometimes for indexing. If you want to say move through an array in memory, you can just keep incrementing that to keep pushing it onto the next value in memory. The last one there is MISC, which is basically everything else that we need to do. And there'll be quite a few odd instructions in there that don't quite fit anywhere else. So if we transfer those values into the table on the right, you can see then the load store move 16 and MISC and increment XY over there. Now I put dots in for the actual arguments to those because we'll cover those later on, but just know for the moment that you have the prefixes there. So you can see that load is prefixed to a 10010, and that gives us 3 bits to actually define exactly what type of load we want to do or whether that load needs to go to. Now if we return to that diagram from earlier on, you can see again that we've got move 8, set AB and GOTO using up 3/4 of the available opcode space, and then ALU takes up another slice. So if we transfer those remaining functions over, you can then basically see how the rest of the opcode space is divided up. And so with that we've covered off all the instructions that are implemented so far in my relay computer. Now if you'd like to actually have a go at programming with these opcodes, you can use my simulator, which can be found at simulator.relaycomputer.co.uk. And on there you can load these opcodes into memory directly and then actually have the computer run them just as my real computer would do. If you need a refresher of what opcodes are available on the computer, there's also a link down there to the instructions page on my Relay Computer blog. And also I'll probably make a PDF out of some of these slides as well as reference as well, and I'll make a link to those. So you might have realised that actually programming the computer is a bit of a pain. And that's because basically you've got to decide what you want the computer to do and then convert that into a list of opcodes and then program that all into the computer. Now basically what you're saying there is you'll have a program that's just full of zeros and ones, and it's very difficult to read through it, especially if you need to correct a mistake or make an alteration. And this is why high-level languages were invented, because it makes it much easier to understand the program and to maintain it and to debug it. And this is where the program instructions are much more like the regular everyday used English, rather than just a list of zeros and ones. This does then mean, of course, we need to have something that will translate between the two, and this is where compilation comes in. But we'll save that all for next time when I'll start covering the assembly language. So this is where it's not quite a high-level language, but it's not quite as low level as just dealing with the zeros and ones. And this will make it much easier to program the computer and to understand what's going on. But for now, that's it. As before, if there's anything you'd like to ask, please do feel free to use the comments and I'll endeavour to get back to you. But otherwise, I'll see you in the next video.